So let's say you want to learn microtonal music theory. So you probably went online, joined a discussion group, or looked into a forum, or watched a YouTube video on tuning theory or some microtonal temperament, and you promptly were left much more confused than you were when you came in. And you were probably hazed with an endless sea of jargon and what looked like absolute gibberish and technobabble from Star Trek, and you just had no idea what the hell was being talked about. Learning microtonal music theory can really suck for a lot of reasons, mostly in that it's a completely novel field with many, many different people contributing to entirely new fields of research and study. And so all of these people are coming up with their own words and definitions and throwing it all together in one big soup, and none of it is standardized. And thus, if you're trying to learn the basics and you come in, you can't get lost very, very easily. This happened to me for a while, and I've seen it happen to many, many other people. This video is going to serve as a guide for at least how I came to understand microtonal tuning theory and temperament theory, and trying to teach you in order all of the major moments of understanding that I've had that led me to improving my composition and writing process. There is so much information out there and so much noise that this will be a useful guide for learning only the things that you really need to learn to begin composing and writing interesting music. Not only that, but even if you had no interest in composing anything outside of 12-tone equal temperament, standard Western tuning, I think this will still give you a lot of insight as to how harmony works as a whole. It will show you how timbre and temperament and composition and chords and sound design and even things like distortion are all interconnected. It will deepen your understanding of everything. Learning about tuning theory has taught me so much about FM synthesis, for example. It's taught me so much about composition and about layering different instruments together and what types of timbres these instruments should be depending on the tuning that I'm in. Because everything in music is interconnected. And the more that you learn about some niche thing in music, it will relate to everything else in some way. The more you learn about one piece, you're actually learning about the whole. It'll also teach you a ton about regular, normal music theory. For me, music theory is always really difficult to learn and get into. I think largely because the most common teaching styles for music theory don't want you to ask a lot of questions. Oftentimes, music theory is taught in a way where they want to abstract away from the math and the physics that underlies everything, and just teach you the abstracted concepts because it's easier and people don't like math. And of course, cultural familiarity matters just as much, if not more, than the mathematics and physics underlying everything. But coming to understand the mathematics of what's happening will leave you without any questions as you learn and study through the process. To learn microtonal music theory, you want to have a generalized, applicable music theory that can apply to any collection of notes. And to do that, you need to go down to the very, very fundamental basics. So we're going to start from ground zero, which is going to be the harmonic series. So as you should know, all waveforms that repeat, all sound waves, all waves in general that repeat from some point to another are going to be composed of sine waves, and all of those sine waves within it are all going to be harmonically related to the fundamental frequency, or which is related to the wavelength of the entire wave. As you can see here in this spectrogram, my voice is speaking at a rate of around 120 to 90 hertz or whatever. So my vocal folds are flapping around at like 100 times per second, right? And then that waveform that's coming out of my mouth and is being shaped by the size of my throat and the placement of my tongue and whatnot, that waveform consists of a bunch of harmonics above it, and all these harmonics have an integer multiple relationship to the fundamentals. So this 100 hertz wave has a harmonic at 200 hertz, 300 hertz, 400, 500, and so on, roughly, right? Now, we're hearing my voice not as a stack of harmonics though, but we're hearing it as a single waveform. That's how we're interpreting it. But the harmonics are there, and it's possible to pinpoint them. So if I change the shape of my mouth and move my tongue around very slowly, you'll be able to hear and pinpoint each of the harmonics within my voice. So I'm just going to say the word ear. We can see that when I say ear, there's this little swooping down formant, little filter guy based on, my tongue movement. And if I just sing a sustained note and say that word very, very slowly, you're going to hear all the individual harmonics. So if I go all the harmonics get highlighted, and you can see in this waveform that the sine waves that make up my voice are going to get louder, and you can start to pinpoint and see where the sine waves are located, right? So the harmonic series is super, super important. Keep that in mind. Now let's talk a little bit about harmony. Our ears and our brains and auditory nervous system can hear and detect frequency ratios of different pitches relative to each other. So if you are to play something 1 octave apart or at twice the frequency, you'll hear something that sounds extremely consonant, right? In fact, it's so consonant and so in tune that when I play them together, the shape of the wave changes a little bit, but it's still playing the exact same frequency. The fundamental frequency of this waveform didn't actually change at all, right? All we've done is change the timbre, actually, of this wave. So let's think about this for a second and break it down, okay? So our first note that we're playing consisted of harmonics above it that are integer multiples related to the fundamental frequency. So we'll say that fundamental frequency is F, right? And then it's going to consist of harmonics at 2 times the frequency, 3 times the frequency, 4 times, 5 times, 6 times, 7 times, 8 times, and so on, right? This just keeps going. Our second note that we're playing is at 2 times the frequency, right? An octave above it. This is going to be playing at an octave above, and then its second harmonic is going to be at 4 times the frequency of this guy, right? Because it's 2 times 2. And then we're going to be playing at 6 times, and then 8 times, and then 10 times, and so on. And then you'll notice that this frequency and this frequency is the same, and this frequency and this frequency is the same, and so on and so forth. In fact, every single harmonic in this waveform is contained within this waveform. This whole waveform is contained within this waveform. And that's why when you play them together, you're not actually playing a different pitch at all. You're just changing the timbre of this waveform. You're just doubling the amplitude of the second harmonic and the fourth harmonic and the sixth and all the even harmonics. So it should come as no surprise that when I play these 2 notes together, you're just getting a change in timbre and you're not actually hearing any other notes, right? Now, if I play a perfect fifth, which in 12-tone equal temperament is 7 steps out of 12, right? What you're going to hear is something that sounds very, very consonant. And there's a little bit of a more complex thing going on here than with the case of the octave, right? Right? With the octave, this is a completely stable, unchanging waveform. And when I'm playing a fifth, we have the slowly evolving, transforming, and kind of phasery sounding combination of notes. It's moving a little bit, right? So a perfect fifth is approximating a 3/2 relationship. It's very, very, very close to 3/2. And the way that an octave is a 2-to-1 relationship of, the second harmonic to the first harmonic, the 3/2 relationship is the third harmonic to the second harmonic. So if you were to take a harmonic series, you're just comparing the distance between the second harmonic and the third harmonic there, right? Now, in 12-tone equal temperament, we're dividing our octave, our 1-to-2 ratio, our doubling of frequencies into 12 equal steps. When you do this, you can get very, very close approximations to other harmonic intervals, but they're never going to be exact in the way that an octave is. And that's simply due to the mathematics of what happens when you divide an interval into even steps. Not a single one of those subdivisions will end up being another harmonic interval. They're all going to be irrational numbers, because when you take an octave and divide it into 12 equal steps in pitch space, you're taking the 12th root of 2. And the 12th root is an irrational number. And we're trying to get to a rational number of 3/2, right? So it happens to be that when you divide that octave into 12 notes, you get very close approximations to some really nice harmonic intervals. So this isn't exactly 3/2. Still sounds pretty damn good though, right? And that's because while our ears and our auditory nervous systems learn to recognize harmonic intervals and relationships between notes, there's still some wiggle room there. There's this blurring of our perception when it comes to recognizing and hearing these intervals due to the faulty and imperfect way that our auditory nervous system is constructed, because we are simply, you know, like organic machines. You know, we're not beings made out of numbers and math. We're beings made out of like neurons and synaptic connections and all sorts of physical stuff holding us all together, right? So we like really nice ratios like 3:2, but we can also handle a little bit of error when it comes to approximating them. In fact, that error can sound really nice. So if we go back to this little thing here and we have our first note, we're going to be comparing this against the 1.5 F. 1.5 is 3/2, and then the second harmonic of that is 3, and then the third harmonic is 4.5 F, and so on. These harmonics are now shared, and these harmonics are now shared. But now we're also introducing new harmonics that didn't exist there before. So as I said, there's this like phasing kind of effect going on, right? If we look at this here, our 3/2 ratio is really not actually 3/2. It's going to be like 2.999 or something over 2, right? It's a little bit, it's just a hair off. And that 2.99 over 2 is going to, you know, extend to this guy, right? So this is going to be 2.99 or something. And then this is going to be over here. The 6F is also going to be like 5.98 or something like that, right? Now, what's interesting is those shared harmonics here, this 3F and this 2.99, ignore everything. I'll just imagine I changed the numbers for everything here. This 3F and this 2.99 are a little bit out of tune. And what happens when you play two sine waves right next to each other in pitch space that are just like a cent off? You get beating, right? The phasing effect that we hear from this, that's the sound of all of these harmonics beating at different rates. The lower harmonics are going to beat more slowly than the higher ones because the higher ones have higher frequencies relative to each other. You'll see that these notes beat much, much more slowly relative to the notes higher up, and it makes a really pretty pattern. And that combined beating effect that's happening up and down the entire frequency spectrum, we're hearing it as that phasey effect. So as I said, in 12-tone equal temperament, there's a little bit of error when it comes to the 3/2 ratio. What happens if we make it perfectly in tune? What does that sound like? So we can use Microtuner, which is a Ableton Max for Live device. We can set this to just intonation, meaning all of our notes that we play are going to be exact, spot on, simple ratios. So if I play that same ratio, there's still a very, very, very slight amount of phasing, I'm going to be honest with you. I think that's just due to this not being a 100% perfect device, but it's pretty much spot on. And then without it, with it, if I play a major chord, it's very, very busy. There's a lot of stuff going on there. If I make it justly tuned, it's so in tune and locked in that it starts quote-unquote buzzing. This buzzing is the sound of those three notes playing together, reconstructing the harmonic series of a note below it. So we take a look at this thing here. When you play something a perfect fifth apart, you're actually constructing the harmonic series of a note that's occurring an octave below or at half the frequency of that first note, right? All of these harmonics appear in the harmonic series of something where the fundamental is at 0.5. And we have 1, and then 1.5F, and then 2F, and then 2.5F, and so on. So you're going to see, okay, we have 1F here, we have 1.5 here, we have 2 here, and so on and so forth. Whenever you're playing two notes together, you're constructing the harmonic series of a note below it. I'm going to get another wavetable, and this is going to be playing a harmonically rich waveform below this chord, right? All of the harmonics of this guy are located in this. Now, when it comes to intervals on a piano roll, whenever you stack an interval on top of another interval, you are multiplying the frequency ratios together. So as we've stated, C to G, or 7 steps in a 12-step roll, is 3 to 2 or perfect fifth, right? 12 steps is an octave. So if we were to move this G up an octave, this is now going to be at 3/2 times 2 above the original note. So this is going to be at 3 times this note, because 3/2 times 2 is 3, right? And if you look closely at our handy-dandy little spectrogram, it starts at exactly the third harmonic, and every single harmonic above it is a multiple of 3. 3, 6, 9, 12, 15, etc., right? Now, if we look at another interval, such as our major third, right? This is a 5 to 4 ratio, right? It's a little bit more complex. 5 against 4, if we move it up an octave, we're multiplying it by 2. This is 5/2. We move it up another octave, this is now 5. Same exact thing here. You can see that this is playing the fifth harmonic, every multiple of 5 above the root. Since we had to move up 2 octaves here, if we play these two notes together, we're playing the harmonic series of a note 2 octaves below. So if we go here, go 2 octaves below, you can see all these notes are contained within that much lower note. This is the case for every single interval. In fact, that's what chords are. A major chord triad is a 4 against 5 against 6 ratio. That's how we characterize and describe this triad, right? That means this is the 4th, 5th, and 6th harmonic of some harmonic series of another waveform. So whenever you're playing a chord, you're building up from the individual notes and creating and crafting the timbre of some much lower note. So if you think about, like, let's say like chord progressions or something, for instance, like let's say we're playing just a perfect fifth, and then we add this major third in a little bit later, right? Sounds like this. It starts off very consonant and simple, and then it gets a lot more complex once we add this guy in. You can think of it as, when you're playing only these two notes, you're hearing 3/2. You're hearing the third and second harmonic of a thing, right? Then you add this 5/4 relationship, which is a little bit more complex, and the relationship that it holds with these two other notes makes it a little bit more complex. And so this ends up updating your brain and telling you, oh wait, this wasn't 2 against 3. This isn't the second harmonic against the third harmonic. This was the 4th harmonic against the 6th harmonic, because now we just added the 5th harmonic right in between. And remember, 4 against 6 is the same thing as 2 against 3. When you start adding notes and then the chords evolve, your brain is updating in terms of where the actual fundamental is and how all of these notes relate to each other in the harmonic series. So if we continue to add notes to this, and then I end up adding, let's add like some really sour note, like right here or something, a minor 6th afterwards, right? The second that note gets added, it gets way more complex. We go from this like pretty consonant thing to something that sounds really sour and dissonant and spooky or what have you. Not only that, you can hear this very obvious like beating that's going on. And that beating is the sound of all of these notes being added together, paints and creates the harmonic series of a note that's at below like 20 hertz, which means it's at rhythmic rate, which means you're hearing the beating as a rhythm, right? So even, now mind you, this has been in 12-tone equal temperament. Even if we justly tune this, you can still hear, even though these are all exactly in tune with different ratios, the harmonic series that you end up constructing at this point ends up being of a very, very low note, and it ends up being a really complex selection of harmonics of that very, very low note. And that's kind of a way that you could think about harmony and dissonance and how notes relate to each other. We have this progression that, you know, we think of it as like, okay, we're adding notes and it starts to get a little bit more dissonant. You can also think of it as we're lowering the pitch of the hidden fundamental that paints this entire harmonic series, and we're constantly updating our brain with more information as to where that's located. Now I'm going to talk a little bit about regular temperament theory and about commas, which is a subject that I don't personally find that useful or interesting in regards to actually composing and creating music. However, there, of course, are an infinite amount of different ways in which you can compose music and examine tuning theory and explore microtonality. This information is still important to understand so that you are able to read more in self-study and figure out what people are talking about when in discussions like online about different temperaments and tunings and the capabilities of them. So we've divided our octave into 12 equal steps, and 7 of those 12 steps gets very, very close to 3/2. In fact, it's so close that it makes all of our lives a lot easier if we just say that it is 3/2. What does this mean? Well, it means that if we were to take this interval and then move this note here up an octave, we're multiplying it by 2, right? So 3/2 times 2 is now 3. This note is now 3 times the frequency of this note, right? Good. What if we move up another 7 notes from here? Well, if we move up another 7 steps, then that means we're multiplying 3/2 by 3/2 again. So this is now 9/4, because 3/2 squared is 9/4. If we octave reduce this or move this down to exist within the same octave as this is now 9/8, right? We can then repeat this process. 9/8 times 3/2 is going to equal 27/16, right? And then we can repeat this process again, and then over here we get 81/32. If we octave reduce this, we get 81/64. Now, something very interesting happens. So given that we say 7 steps equals 3/2, it naturally follows that 4 steps will equal 81/64. However, we've also stated that 4 steps here, C to E, equals 5/4. Now, if we look at 81/64, this doesn't equal 5/4. We have a discrepancy here. We have an issue. Now, keep in mind, 5/4 is the same thing as 80/64, right? 80/64, this reduces down to 5/4. So these are very, very close together, but because we are approximating intervals here, and we're not playing with these exact frequency ratios, we end up blurring the lines between these two intervals and equating them and make them equal each other. So the difference between these two intervals is called a comma, and that comma is tempered out or removed, equating these two intervals whenever they appear. So whenever, via, you know, this math that we're doing of stacking different notes and equating different things, whenever this interval appears, it's going to point to the exact same note as this interval. This is just a mathematical fact of how 12-tone equal temperament works. Now, do you need to know what commas are to make music? No, you don't. This really isn't necessary, but it helps to have an understanding of where the basis of harmony comes from, why we temper things, and why other temperaments and other divisions of an octave work. Now, Wikipedia defines a comma as a very small interval, the difference resulting from tuning one note 2 different ways. So, as I said, E is the result of stacking 4 perfect fifths. It's also the result of just taking 5/4. So this is called a syntonic comma, which is, quote-unquote, the difference between a just major third, which is 5/4, and 4 just perfect fifths, 3/2, less 2 octaves. That's after we octave reduced it 2 times, right? There's one other comma that you may see mentioned a lot, and it's called the Pythagorean comma. This is the difference between 12 fifths and 7 octaves. Meaning, if you stack 12 fifths on top of itself, you're going to get a note that's extremely, extremely close to 2. Very close, but it isn't 2 exactly. So we temper them. So 12-tone equal temperament, its origins isn't someone just deciding all willy-nilly, hey, what happens if we just divide an octave into 12 notes and write around in it? No, what happened first was people stacked perfect fifths on top of itself because they sounded good. And then notice, when you stack 12 perfect fifths, you get very, very close to an octave. And so if you temper out that difference between the 12th stack of fifths and the octave, you get 12-tone equal temperament, which then gives you a perfect circle of 12 different fifths to move through. The difference between 12-tone equal temperament and 12 equal divisions of an octave, while they are like pretty much identical in that they're all the exact same notes, the difference is the lens at which you examine them and how they were constructed. 12-tone equal temperament is the lens of which your notes are all constructed by stacking fifths that end up being tempered such that they all become equal. 12 equal divisions of an octave is you just take an octave and then divide it into 12 notes. In practice, they're the same thing, but it's about the lens at which you examine and talk about it. Temperaments are mathematical objects, right? They're just made up ways of examining approximations of intervals that have an error to it, and you can examine and see what the consequences are of those errors when you end up stacking and adding intervals together and constructing chords and whatnot. This is all what regular temperament theory is about. For me, none of this is actually that useful at all beyond just understanding what the fuck people are talking about when they're talking about commas and temperaments and whatnot. It's necessary to learn so that you can navigate reading about this stuff, so that you can filter through and figure out what information is important and what information you don't really care too much about. So there are also physical consequences that can arise from temperaments or inaccurate tunings of just intervals that can affect your mix and your master. So we have we're just going to play a justly tuned major third here, which is a 5/4, right? Which means these are the 4th and 5th harmonics of some undertone wave. If we saturate and distort and shape the entire wave, right? So we have these two waves playing together, and they're playing such that both of the waves together repeat every 5 repetitions of one and every 4 repetitions of the other, right? If we distort and shape and smush that wave, we're going to end up creating harmonics of that larger cycle, right? So if we saturate this, you're going to end up getting these undertones. And if we look at an oscilloscope at the same time, it makes sense why that would be the case, right? You know, the whole entire thing is going to repeat at, 67 hertz or whatever. So when you end up distorting this thing that repeats at 67 hertz and shaping it, you're going to get overtones of the thing that repeats at 67 hertz. Now, this is a justly tuned major third, so it's exactly 5/4. What happens if we make it the normal tempered 12-tone equal temperament major third? You end up getting these crazy inharmonic overtones underneath and above throughout the entire frequency spectrum. Those inharmonic overtones are coming from the fact that this isn't playing exactly 5/4. These are actually all harmonics of some extremely low fundamental. So this is called inharmonic distortion. And it's called that because when you distort, like a chord, you're going to get inharmonic, subharmonics, and harmonics based on how long it takes for those tempered intervals to actually complete an entire cycle. So the distortion itself isn't actually inharmonic. The distortion is fully harmonic and is just going to create overtones above whatever the fundamental is of the waveform that's being constructed. What's inharmonic is the chord that you're playing when you're playing in a temperament, because a temperament is approximations of some inaccurately tuned just interval. So the distortion is just going to exaggerate what those inaccuracies are by creating overtones of whatever the true quote-unquote fundamental is, right? So if you play a perfect fifth in 12-tone equal temperament, and the phasing effect ends up repeating every 2 seconds, and then you end up saturating that perfect fifth, you're going to create overtones of 2 hertz, because that's the true quote-unquote length of the entire cycle. This is why on a master, after you have clipped or limited or saturated or done any wave shaping whatsoever to your master, you're going to end up getting mud in your low sub frequency region, even though you may have EQ'd all of that mud away. It's an inherent part of the wave shaping that happens when you are heavily limiting or saturating something. This is why you can EQ out all of the low end from a drum loop, and then you can saturate it somewhere later on in the chain, and then the low end reappears. So what does this mean? It means that your temperament or tuning can have direct effects on how nonlinear distortion works and other effects. Chords can sound drastically different under distortion depending on the temperament that you're using. So if you're using triads that have really in tune perfect fifths in one temperament, it can sound a lot better under distortion than triads in another temperament where the fifths are a little bit more out of tune. So the way that you approach mixing can also change depending on how you're tempering your intervals. It's all interconnected. So something that's very important is how well you can approximate prime numbers or prime harmonics. So in an EDO, or an equal division of an octave, you are equally dividing the number 2, right? So 2 is going to be perfectly in tune, right? So 2 equals 1200 cents. When you go up by 1200 cents, you're multiplying your frequency by 2. Our approximation for the third harmonic is going to be 1900 cents. Now the actual third harmonic is actually 1902 cents. Now, using these 2 numbers, we can start creating more intervals. So 3 over 2, 3 divided by 2, is going to equal 1900 cents minus 1200 cents. This is equal to 700 cents, which is close to 702 cents, the true actual perfect fifth. Now let's get 9 over 4, and we can get 9 over 4 by multiplying 3 over 2 against itself, right? So 9 over 4 in 12-tone equal temperament, we're going to add 700 against 700, which is 1400 cents. This is close to the true 9 over 4, which is going to be the true 3 over 2 multiplied against itself, right? 1404 cents. So this is actually 4 cents flat. Now we can freely divide this by 2 again to get 9 over 8. And to do that, you simply subtract 1200, 200 cents, which is close to the true 9 over 8, which is 204 cents, right? So what you can see from this is, using just our knowledge of what 2 is and what 3 is approximated in our temperament, we can create approximations for every single interval that is composed of 3 and 2. Right? So everything that involves a power of 3 and a power of 2, you can create. Now, it's a mathematical fact that every single number is made up of prime numbers. All numbers are either prime numbers or composite numbers, a collection of prime numbers multiplied against each other, right? Now, the important thing to realize is our approximation of 3 is about 2 cents flat, right? That means any approximation of 9 is going to be 4 cents flat. Any approximation of 27 is going to be 6 cents flat, and so on. Every power of 3 is going to increment how out of tune it is based on what our approximation of that original prime number is. This goes for every single prime number. So in 12-tone equal temperament, our approximation of 5 is something like 15 cents flat, right? That means our approximation of 25 is going to be about 30 cents flat. So the damage that you have in terms of approximating individual prime numbers tells you about how you're going to approximate every single number imaginable. So all you really need to know is how well all of the prime numbers are approximated, and then that can tell you a massive amount of information about how your temperament is going to sound. Now, when I'm composing, I'm not thinking about these numbers whatsoever. This is like an absolute nightmare to actually try to conceptualize and write music to, in my opinion. Some people do it. Some people work with numbers and just intonation. Me, what I do is I use these numbers to understand largely what different temperaments are capable of and what they qualitatively sound like, what emotions they're capable of conveying. Music is a qualitative, emotional, human experience. It isn't a bunch of numbers. It isn't just math, right? So all that really matters is just like, what sounds is it capable of making? We use numbers to understand what those sounds are, but really all that matters is, you know, does it make me feel good when I hear it? So let's take a look at the Zen Wiki, and I've just pulled up the 17 notes per octave page. One of the first things that you're probably going to do is you're going to take a look at how well approximated all the prime harmonics are and what the damage looks like, right? Now, our perfect fifth in 17 Edo is 4 cents sharp. Now, usually we're all very used to hearing fifths that are flat because in 12 Edo, our fifth is 2 cents flat. So this is a little bit more out of tune, right? So this is going to have some consequences in terms of how chords will sound, how distortion will sound on chords and triads and all of that. And also the fact that it's sharper instead of flatter is psychoacoustically very interesting just based on the cultural phenomena that we all have of being so used to things being flatter. The sharper fifth has its own unique particular sound, and all temperaments that have a slightly sharper fifth sound a little bit more similar to each other. This is a way that you can categorize them. Of course, the fifth, the approximation of 3 is like by far, I think, the most important and tells you plenty about how to analyze different temperaments. So 17 Edo has a fifth that is about 4 cents sharp. If you are to look at, say, 22 Edo, you have a fifth that is 7 cents sharp. Since they're both sharp, there's some similarities in sonic quality in how these two different temperaments sound. Even though they're still very, very different from each other and are capable of very different things, they also share a lot of similarities in terms of what they are also capable of. I think that about covers it for now. I think the video is getting long enough, and that's plenty of information to digest. So let's just run through the main bullet points that we need to remember. All harmony is based on the harmonic series. You know, harmony, harmonic series, the word comes from that. Every note is composed of a bunch of harmonics, and when you play notes together, you are creating the harmonic series of a note underneath, which is an entire lens of which you can understand chord construction and harmony and chord progressions and whatnot. So our brain can hear and detect frequency ratios between notes, and these ratios don't need to be 100% accurate. You're allowed some wiggle room. This wiggle room, or, you know, the damage of approximating these intervals, can have interesting psychoacoustic consequences on how different chords sound. So you can take a 4 against 5 against 6 ratio chord, which is a major chord, right? And you can approximate all those 3 harmonics in slightly different ways. So that chord, if you were to construct it in 17 tone equal temperament instead of 12 tone, you know, 17 also will approximate those same intervals, but in slightly different ways. And so it'll still sound like a major chord, but it'll have a little bit of a different color and flavor to it than in 12. Same thing goes for other temperaments like 19, 22, 31, etc. They all can create some of the same chords, but they have a little bit of a different flavor. And that flavor might sound jarring to someone who's never heard these sounds before, but your ear can very quickly become accustomed to it, and then it ends up just sounding natural, and you end up accepting the sounds that are presented to you, because consonance and dissonance are cultural phenomena. We also talked about commas and regular temperaments, which are mathematical objects that allow you to map different notes to different intervals. And then you can see the consequences of what happens when you multiply different intervals together within these temperaments, and you can see which intervals end up equating. By finding out which commas are tempered in certain temperaments, you are able to classify different temperaments in different ways. So any music that is dependent on the existence of some comma being tempered out is going to be one-to-one translatable into another temperament that also tempers out that comma, right? So if you stack a perfect fifth 4 times, and that gives you your major third, and that exists in 12 tone equal temperament, this also translates over into another tuning that does this, like 17 tone equal temperament. They both cancel out the exact same comma, thus you can translate music directly between the two. And then we also talked about the physical consequences of what happens when you temper different intervals and you have inaccurate approximations of just intervals. This comes into play especially with things like distortion, right? So inharmonic distortion occurs when you are performing some sort of nonlinear processing or wave shaping, saturation, limiting, whatever, to chords or intervals that are inaccurate approximations of a just interval. So what that means is that when you're writing in a temperament, the timbres that you're using, the way that you mix and go about composing your song, and the sound design that you specifically choose for the sounds that you have, all are dependent on the temperament that you're using. It's all interconnected. That's something important to keep in mind when you are carrying on in the composition process and knowing what types of sounds are going to work best for different types of temperaments. You're not going to want to slam power chords in temperament that has a really shitty perfect fifth, right? So that's pretty much the video. It ended up getting a little bit dry, but this is all really important prerequisite information before we start getting to the more fun stuff. So the next video is going to be about scales and scale construction and actually, oh boy, writing music. So that's what this is all about. Even though numbers can be fun, we don't really care about the numbers. What we care about is actually writing music and creating and exploring cool, novel, new sounds. So that's what we're going to do next time. This is all important information so that we can get to that fun spot. If you want to support the channel, then you should subscribe if you're not already. I have a Patreon. You can give me money. I would like money. That would be cool. And please leave comments if you have any questions or criticisms or corrections on anything that I've said. All right, thanks. Bye.